In this video, we're going to talk about populations and sampling. A population represents an entire group of observations that we want to make conclusions about. For example, a population of students at a particular university. We often don't observe the entire population, so we collect a subset of that population, called a sample, to help us draw conclusions about the population of interest. Statistical inference is the process of using sample data to make conclusions about the underlying population the sample came from. Under the umbrella of statistical inference, we have both estimation and hypothesis testing. Suppose we want to ask an inferential question. For example, what proportion of students on campus use a Mac? If we don't have data on the entire population, how can we answer this question? Well, we collect a sample. That sample should be random, such that each sample of that size has an equal chance of being selected, and representative of our target population, so that we can generalize our findings. Parameters are quantities that describe a population. For example, the proportion of all students on campus who use a Mac. Parameters are often not observed, as we may not observe the entire population. For example, say that we knew the true population proportion of students on campus that use a Mac is 0.4. Statistics are quantities that describe a sample. For example, the proportion of a sample of 100 students on campus who use a Mac. These are sometimes called point estimates. For example, from a random sample of 100 students on campus, the sample proportion of students who use a Mac is 0.42. Now, will all samples have the same estimates? Not necessarily. Say we have sample 1, and we observe that 43% of students use a Mac. We could collect another sample, sample 2, with different students, and find that only 39% of students use a Mac. Now, neither of these numbers are incorrect, but these differences between samples taken from the same population refers to something called sampling variability. Ideally, along with a point estimate, we also report a plausible range of values for the parameter of interest. For example, a statement like, we expect between 35 and 45% of students on campus to use a Mac. Now, this range depends on sample size. As sample size increases, sampling variability decreases, and statistics more closely reflect population parameters. It also depends on how the observations of our population of interest are distributed. A sampling distribution describes a distribution of many estimates calculated from many samples from our population. Say we take 1,000 random samples from our population, each of size 100. We could then look at the distribution of the proportions, the sampling distribution of the sample proportion of students who use a Mac. So, if we take 1,000 samples of size n is equal to 100, each of them will have their own sample proportion, which varies from sample to sample. If we plot all of these sample proportions, we can visualize the sampling distribution of the sample proportion, which helps us conduct statistical inference.